Hello, everyone. My name is Naveen Joy, and I'm an engineer at Cisco. So my team and I, we have been building and supporting a Kubernetes cluster on OpenStack. And today I wanted to share some experiences with respect to networking and the overall architecture. So first, why Kubernetes? Kubernetes provides a higher level abstraction to a lower level Docker interface. You can think of Kubernetes as a management layer above Docker. Even though Kubernetes supports multiple container platforms, I'll be focusing on Docker here. So it deals with a lot of orchestration issues, like if you want to run containers, if you want to delete them, if you want to scale out. So Kubernetes takes that responsibility. So you have the ability to organize your applications that are running in Docker containers into pods. So pods form the basic unit of operation in Kubernetes. Now, what exactly is a pod? Let's say you want to run an application inside a virtual machine, let's say typically an app server. And there are several components of it. One is the app server itself. You may have a logging component, and you may have a caching component. So now you can create a container version of all of these apps and then group that into a pod. It's like a set of one or more containers. Now, Kubernetes will now take care of managing that pod. Keep in mind that a pod is not intended to be running multiple instances of the same application. For instance, you will not be running multiple web servers in a single pod. So you will have multiple pods for doing that. So the way you do it is you declare the end state using a pod manifest. Much like if you're familiar with heat, you declare a end state with a heat template. Here you have a pod manifest. And then Kubernetes will now ensure that if the end state changes, if the actual state changes from what you have declared, let's say an application that is running in your pod develops a fault and it fails, Kubernetes will now make sure that that application is restarted or that container is restarted in order to attain the desired state equals running that you've specified. It also provides a scheduling mechanism for pods. And the containers in a pod are tightly coupled, which means it's co-located on a host, and it will share the network namespace, the volumes, and also the host name. This is one interesting feature that I've seen, is the ability to group pods using labels. Let's go back to the previous example, where you have multiple pods. And you can group them together using a label, and then Kubernetes can now, using that label, load balance your traffic across multiple pods. You can enable access to a pod now using a service abstraction. So now the thing is, once you have a pod, it's being scheduled onto a host. The pod has an IP address. And who keeps track of that IP address? Let's say the underlying virtual machine fails. Kubernetes has restarted a pod on a different virtual machine. It will get a different IP address, right? So now who is responsible for keeping track of that? If that particular pod is running your middle tier, is your web application responsible for keeping track of all the IP addresses that are changing? The answer is no. So Kubernetes provides a service abstraction, which does that. It provides a stable service virtual IP address. And that stable service address is the entry point and the exit point for the traffic. And when traffic hits the service virtual IP, it will be proxied to one of the backend pods. Kubernetes can do pod management as well. It can restart a failed container in a pod automatically. Does some self-healing. Let's say the underlying virtual machine that is running your pod fails. Kubernetes can then figure out another virtual machine, restart or recreate your pod on another virtual machine. And you can also do horizontal scaling. So here is, if I were to picture the overall architecture that we built, this is the network diagram. On the left-hand side is how you talk to the system. You have the pod manifest, and you have the service manifest. And you send that manifest to the API server. And in order to do that, Kubernetes has a client called kubectl. And on the right-hand side, you have the worker nodes. These are the machines that are available, the virtual machines that are available to run your pod, basically the Docker host. So in that virtual machine, you run kubelet. And what kubelet does is a program that you run, which basically talks to the API server and registers that virtual machine. They'll say, I'm there. You can schedule pods onto me. And then the kube proxy provides a service abstraction. It takes care of a proxy functionality where inbound traffic is now proxied to the backend pod. So you don't really have to know, your application doesn't have to really know about the IP addresses of the pods. The kube proxy will take care of that translation. Then you have other core components, like, of course, the API server and the controller manager. So much like how you have the various control loops to enforce the desired state, right? You have said that you want the pod to be running. The controller manager is a component that is going to monitor your pod to make sure that if the underlying host fails, if you're turned on the replication controller, it's going to create another replica of it, because you have decided that the intended state is to run at least one replica. And the scheduler component, which is going to schedule your pod to an available instance that has resources. Now, networking model. Let's look at the default networking model in Docker. Most of you may be already familiar with this, but it's host private networking. What Docker does is it creates a bridge named Docker 0 on each virtual machine, and it allocates a private subnet from RFC 1918 for that bridge, and attaches each container to Docker 0 using a virtual Ethernet device, and assigns an IP from that private subnet to the container, and sets the bridge as the default gateway. Looks like this. So you have the virtual machine, Docker 0, and the containers inside. So do you see a problem here? So all the Docker 0s are the same, most likely will have the same subnet. So when container C1 here talks to C4, there has to be a way of the actual, we will look at the next slide, it has to be NATed, the traffic. So container reachability. Since Docker allocates the same IP addresses to containers, containers can talk to each other on the same machine, no problem, but traffic cannot be routed directly across hosts using their private IPs. So containers communicate across hosts using DNAT. The host IP and port is translated into container IP and port by Docker. So this can pose problems for apps. So it's kind of a pretty hard problem now. You'll have to take your app and lift it to a container level. If you use a default networking model, you have to coordinate port allocations. If you are sharing hosts between developers, if you're using dynamic port, service discovery and application configurations will pose problems, because a container that is running inside a virtual machine will not be aware of its IP address when it talks outside, because that's NATed. Some applications, as a result, will break if you need to register your IP, right? There's no way that you can register your IP. You don't know the IP. And apps that perform IP-based access control and authentication will break. So how do you fix this? So in Kubernetes, containers communicate directly over a routed IP network without using NAT. So a container sees the real IP of another container, and the host sees the real IP. So there's full IP connectivity. So now you'll have to modify the default networking model of Docker for Kubernetes to work. So how is networking done in Kubernetes? So for each pod, you create a routable IP and assign that IP to the pod. All the containers within a pod share the network namespace, including the IP address and port. How do you implement this? So the default bridge for Docker, that is removed, and it is replaced with a container bridge, CBR0. And what Kubernetes does is it creates a pod container, kind of a holding space, and it networks all the other containers within the pod to that pod container using an option within Docker called, you can pass --net equals container. So that using that container function, all of these app containers are networked together into that pod. So each VM is assigned a subnet for pod networking. So note that this is in addition to the subnet that is used by Neutron. So the virtual machine itself is plugged onto a subnet. And you can think of a little network inside the virtual machine, which is for the pod that you'll have to allocate. And you replace the Docker 0 bridge with CBR 0. And you tell Docker to use this CBR 0 instead of Docker 0 by using the -- bridge equals CBR 0 in its options. So once you do that, any container that you create using Docker will be assigned an IP from this host pod subnet that you allocated. How do you route pod subnets? Option 1 is to create routable pod networks. Configure instances to forward IP packets. This is done by default, though. So, second is to add static routes on the L3 Neutron gateway to route traffic to the instance. So one more thing I noticed is when security groups is enabled, Neutron will ensure that traffic is restricted to the instance. So you will have to add this IP tables rules to permit inbound and outgoing traffic from the pod CIDR network. It looks like this. So you have 2 instances and 2 pods in each instance. You allocated a pod subnet, and you have added routes on the gateway to route traffic, so you have full reachability between the containers. Option 2 is to build an overlay network to route pods. So this is still in an experimental stage. What it does is it creates another layered virtual network architecture to connect the pod networks together. So you have open source options like Flannel, Weave, and Calico. Flannel is designed for Kubernetes. It creates a pod subnet and then uses etcd to maintain the subnet to host mapping. And then it builds an overlay mesh network between instances using UDP tunneling. So in order to get this to work, you'll have to enable UDP. You have to allow UDP port 8225 on the instance security group, and also adjust MTU size to prevent fragmentation. So if you're using option 2, the network looks like this. You have this Flannel daemon that's running in each host that is building an overlay network that is tying up the 2 pod subnets, various pod subnets inside the host. So if you're using a Neutron overlay like VXLAN or GRE, this Flannel overlay will use a Neutron overlay as its own underlay. You can say this layered overlay network architecture could pose performance issues. So ensure that you test it out before you deploy this in your infrastructure. So conclusion, a lot of possibilities here, pretty interesting. Check out Kubernetes. The documentation is evolving but good. Contains several examples. That's where I started. So you can deploy those templates, service templates, the manifest, service manifest. There are a number of manifests available. And also salt stack scripts are available to automate the whole thing. So that's it, and thank you.